Here is a sentence that sounds like it should be straightforward. The most distant galaxy ever observed is about 32 billion light-years away. Read it again. 32 billion light-years. The universe is 13.8 billion years old. Light travels at the speed of light. So how can anything be 32 billion light-years away if the universe has only had 13.8 billion years for light to travel? The answer to that question is not a correction or a mistake. It is an introduction to the fact that distance in the universe does not mean what you think it means, that the word away is doing something in that sentence that it has never done in any sentence you have ever read before, and that the concept of distance, which works perfectly well for everything from the width of a room to the diameter of the solar system to the span of the galaxy, quietly breaks down when applied to the universe as a whole. Not because our instruments are imprecise or our mathematics is incomplete, but because the universe itself is doing something to space that makes the ordinary concept of distance inadequate at large enough scales. Tonight, we are going to find out exactly what that something is, why it makes the word distance stop making sense, and what it means for the actual size and structure of a universe whose extent is, by any honest measure, beyond what language was designed to hold. Welcome to Dusk and Discovery. This one changes how you see the sky. Get comfortable because by the end of tonight the night outside will look different from how it looked before. Subscribe if you want more nights like this. Now, let us find out what the universe is actually doing to space. Start with what distance means in ordinary experience, because the failure of that ordinary meaning at cosmic scales is not apparent until you understand what the ordinary meaning actually is. When you say that the nearest coffee shop is 400 meters away, you mean something specific and unambiguous. There is a path through space between you and the coffee shop. The length of that path, measured in meters, is approximately 400. You could in principle lay a ruler end to end along that path and count the ruler lengths. The measurement does not depend on when you make it in any important way. The coffee shop is 400 meters away now, and it will be 400 meters away tomorrow, and the 400 meters refers to a specific, stable, measurable spatial interval between two objects in a world that is, for practical purposes, not changing its geometry underneath you while you measure. Even for large distances within the solar system, this concept holds. The distance from Earth to the Sun is approximately 150 million kilometers, and that number refers to the length of the path through space between the two objects at any given moment. The path exists in a well-defined sense. The distance is measurable by multiple independent methods, from radar ranging to the timing of spacecraft trajectories to the geometry of planetary orbits, and these methods agree. The solar system is not static. The planets are orbiting, and the distances change continuously as they do. But at any given moment, the distance between any two bodies in the solar system is a well-defined and measurable quantity that matches our ordinary intuition about what distance means. For distances within the Milky Way, the concept begins to require more careful handling, not because it breaks down, but because the methods for measuring it become more indirect. Stars are too far away for radar ranging. The primary method for nearby stars is parallax, the apparent shift in a star's position on the sky as the Earth moves around the Sun over the course of a year. The size of the shift is inversely proportional to the distance of the star, and for the nearest stars the shift is measurable with ground-based telescopes and with exquisite precision using the Gaia Space Telescope. For stars further away, the parallax becomes too small to measure directly, and other methods take over. The period luminosity relationships of Cepheid variable stars, which allow their intrinsic luminosity to be inferred from the period of their brightness variation. The properties of main sequence stars in star clusters, which allow distances to be inferred from the difference between the observed brightness and the intrinsic brightness expected for that type of star. The spectra of individual stars, which encode information about their luminosity class and therefore their intrinsic brightness. All of these methods are building blocks of what astronomers call the cosmic distance ladder, a hierarchy of measurement techniques in which the calibration of each step depends on the methods below it. Parallax calibrates Cepheid distances. Cepheid distances calibrate the distances to nearby galaxies. The distances to nearby galaxies calibrate the properties of type Ia supernovae, which are bright enough to see across billions of light years. The type Ia supernova distances calibrate the relationship between redshift and distance that allows the redshift of a galaxy's spectrum to be used as a distance indicator for the most remote objects. Each rung of the ladder extends the reach of the previous one, and each rung introduces its own uncertainties that propagate up through the system. Throughout all of these methods, the underlying concept of distance remains approximately the same as in ordinary experience. The distance to a star is the length of the path through space between us and the star at the moment of measurement. The measurement is complicated by the fact that we can only observe light that left the star in the past, so we are always seeing the star as it was, not as it is. But for stars in the Milky Way, the light travel time is at most 100,000 years, short enough that the galaxy's geometry has not changed significantly during that time. The concept holds. The distance ladder works. The numbers it produces are stable and self-consistent and interpretable in the ordinary way. And then you get to the scale of galaxy clusters and superclusters and the observable universe as a whole, and the concept begins to require a qualification that turns out to change everything. The qualification is this: the universe is expanding, and the expansion is not the expansion of matter through a fixed space, but the expansion of space itself. And when space is expanding, the concept of distance becomes ambiguous in a way that has no analog in ordinary experience, and that requires careful specification of what exactly you mean before any number you state can be unambiguous. The expansion of space is one of the most important and most frequently misunderstood facts in cosmology, and getting it right is essential for understanding why distance stops making sense at large scales. The misunderstanding usually takes the following form. People hear that the universe is expanding and assume this means that the galaxies are flying through space away from each other, like shrapnel from an explosion, with space itself remaining fixed and the matter in it moving. This picture is wrong in a specific way that matters enormously. In the correct picture, the space between galaxies is itself expanding. The galaxies are not moving through space. The space between them is growing. The distinction is not semantic. It has physical consequences that are qualitatively different from what the shrapnel picture predicts. The clearest way to see the distinction is through the analogy of dots on a balloon being inflated. Imagine dots drawn on the surface of a balloon that is being blown up. As the balloon inflates, the dots move apart, not because the dots are moving across the surface of the balloon, but because the surface itself is expanding. An ant living on the surface of the balloon would observe all other dots receding, and would observe more distant dots receding faster in proportion to their distance, exactly as we observe in the universe. But the ant's observation that the other dots are receding does not mean the ant is at the center of the expansion. Every dot sees every other dot receding. There is no center. The expansion is a property of the surface itself, not a motion of the dots across a fixed surface. This is the Hubble expansion, first observed by Edwin Hubble in 1929 from measurements of the redshifts of nearby galaxies. Hubble found that the recession velocities of galaxies are proportional to their distances, a relationship now called Hubble's law. The constant of proportionality is the Hubble constant, denoted h0, currently measured at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec, roughly 3.3 million light-years, of distance between us and a galaxy, that galaxy appears to be receding at 70 kilometers per second. A galaxy 10 megaparsecs away appears to be receding at 700 kilometers per second. A galaxy 100 megaparsecs away appears to be receding at 7,000 kilometers per second. A galaxy at roughly 4,000 megaparsecs, or about 13 billion light-years, appears to be receding at the speed of light. That last sentence requires immediate unpacking, because it seems to violate the fundamental principle of special relativity that nothing can travel faster than light. The resolution is that special relativity's prohibition on faster-than-light travel applies to motion through space, not to the expansion of space itself. A galaxy that appears to be receding at the speed of light is not moving through space at the speed of light. The space between us and it is expanding at a rate that makes the total distance between us increase at the speed of light. The galaxy itself may be moving through its local space at a modest velocity of a few hundred kilometers per second. The recession velocity that Hubble's law predicts is not a velocity through space, but a rate of change of a spatial separation due to the expansion of the space itself, and this rate of change is not bounded by the speed of light. Galaxies beyond the Hubble sphere, the sphere at which the recession velocity equals the speed of light, are currently receding from us faster than light. The space between us and them is expanding faster than light can cross it. This means that light emitted by these galaxies right now, heading toward us, is currently losing ground. The distance between the photon and us is increasing even as the photon moves toward us at the speed of light through its local space. Whether that photon will ever reach us depends on whether the expansion of the universe will continue to accelerate, decelerate, or remain constant. In a universe with a cosmological constant, as ours appears to be, the expansion accelerates, and light emitted today from galaxies beyond a certain distance will never reach us, because the space between them and us will expand faster than the light can cross it for the entire future of the universe. This brings us to the first place where the word distance stops making sense. The Hubble sphere, the boundary at which recession velocities equal the speed of light, is at approximately 14 billion light-years. Beyond that boundary, galaxies are currently receding faster than light, and yet we can observe galaxies that are currently much further away than 14 billion light-years, galaxies that are currently 40, 45, even 47 billion light-years away. How can we see something that is currently beyond the distance at which light can reach us? The answer is that we are not seeing those galaxies as they currently are. We are seeing them as they were, billions of years ago, when the light now reaching us was emitted. At the time that light was emitted, those galaxies were much closer to us than they are today, close enough that the light they emitted could begin its journey toward us and make progress even against the expanding space. The space has expanded enormously since then, carrying both the emitting galaxy and the photon outward, but the photon has been making progress toward us the whole time, and it has now arrived. The galaxy that emitted it is now 47 billion light-years away, but it was much closer when the light left it 13 billion years ago. This is the first layer of ambiguity in what distance means at cosmic scales. When someone says that a galaxy is a certain number of light-years away, they might mean the distance at the time the light was emitted, or the distance right now, at this moment, even though we cannot actually observe the galaxy at this moment, because the light currently leaving it will not arrive for billions of years. These two distances are very different, and neither of them is the distance in the ordinary sense of the word, because neither of them refers to a stable, unchanging spatial interval between two objects in a fixed space. Cosmologists have developed a vocabulary for distinguishing between these concepts, but the vocabulary is technical and not widely known outside the field. The comoving distance to a galaxy is the distance that would be measured right now, at this moment, if you could somehow freeze the expansion of the universe and lay a ruler end to end between us and the galaxy at the current moment. The comoving distance to the most distant observable galaxies is approximately 46 billion light-years, which is why people say the observable universe has a radius of about 46 billion light-years. This number is the comoving distance to the cosmological horizon, the surface beyond which no light has had time to reach us since the Big Bang. The look-back time distance is the time elapsed since the light was emitted, multiplied by the speed of light. It is the answer to the question of how long the light has been traveling. For light from the most distant galaxies, the look-back time distance is approximately 13.8 billion light-years, which is also the age of the universe in years times the speed of light. This is the number you might naively expect for the size of the observable universe, if you thought of it as the sphere that light has had time to cross since the Big Bang. The luminosity distance is a third concept, defined as the distance you would infer from the brightness of an object if the universe were not expanding and space were Euclidean. Because the expansion of the universe redshifts light, reducing the energy of each photon and reducing the rate at which photons arrive, distant objects appear dimmer than they would in a non-expanding universe. The luminosity distance accounts for this effect, and it is the distance that is most directly relevant for measuring the intrinsic properties of distant objects from their observed properties. The angular diameter distance is a fourth concept, defined as the distance you would infer from the angular size of an object of known physical size. In a non-expanding Euclidean universe, an object twice as far away would appear half as large in angle. In the expanding universe, this relationship breaks down for objects at very large distances, and the angular diameter distance is the effective distance that gives the right answer for angular sizes. Remarkably, the angular diameter distance does not increase indefinitely with redshift in the expanding universe. It reaches a maximum at a redshift of about 1.6 and then decreases, meaning that objects at very high redshifts actually appear larger in angle than closer objects of the same physical size. This counterintuitive result is a direct consequence of the expanding universe and has been confirmed observationally. These four distance concepts, comoving distance, look-back time distance, luminosity distance, and angular diameter distance, are all different numbers for the same galaxy. They measure different things, and the right concept to use depends on what question you are asking. There is no single unambiguous answer to the question of how far away a distant galaxy is, because the question itself is ambiguous. The ambiguity is not a failure of our measurement techniques. It is a feature of the universe itself, a consequence of the fact that space is expanding, and that the expansion is not uniform over the time it takes light to travel cosmological distances. The concept of distance becomes even more fraught when you consider what happens to the light during its journey. A photon emitted by a galaxy 12 billion years ago was not traveling through the space of 12 billion years ago. It was traveling through a sequence of spaces, each slightly different from the previous one, as the universe expanded during its journey. The photon traveled through space that was denser and smaller when it was emitted, then through space that was progressively less dense and larger as the universe expanded, and it arrived in the space of today, which is much larger than the space through which it began its journey. The total distance traveled by the photon is not the current distance to the galaxy, not the distance at the time of emission, and not the age of the universe times the speed of light. It is an integral over the expansion history of the universe, a calculation that requires knowing the expansion rate at every moment of cosmic history. The expansion history of the universe is encoded in the Friedmann equations, the equations of motion for the scale factor of the universe derived from Einstein's field equations of general relativity, applied to a homogeneous and isotropic spacetime. The scale factor is a function of time that describes how the overall size of the universe changes, and its time dependence is determined by the energy content of the universe, including matter, radiation, and dark energy. The Friedmann equations tell us that the universe expanded very rapidly in the early phases when radiation dominated, then more slowly when matter dominated, and is now accelerating due to the dark energy that constitutes roughly 68% of the universe's total energy content. The expansion of the universe is not uniform. It has been slowing down and speeding up over cosmic history, and the current acceleration due to dark energy is a relatively recent development in cosmic time. For the first roughly 7 billion years of the universe's history, the expansion was decelerating under the gravitational influence of the matter content. For the past roughly 6 to 7 billion years, the expansion has been accelerating as dark energy has come to dominate the energy budget. The transition from deceleration to acceleration occurred when the matter density, which dilutes as the universe expands and the volume increases, dropped below the dark energy density, which remains constant as space expands. Before that transition, the fate of the universe was uncertain. After it, the future is sealed. The expansion will accelerate forever. Dark energy will dominate the energy budget more and more completely, and the universe will approach an exponential expansion in which the distance between any two unbound objects doubles in approximately 10 billion years, indefinitely. The effect of this expansion history on the concept of distance is cumulative. Every calculation of a distance to a remote galaxy must integrate over this expansion history, accounting for the changing expansion rate at every moment of the photon's journey. The result is a set of distance measures that are complicated functions of the redshift of the galaxy and the cosmological parameters of the universe, functions that have no simple intuitive interpretation in terms of ordinary notions of spatial extent. The complexity is not a deficiency of the theory. It is an accurate reflection of the actual geometry of an expanding universe with a specific expansion history. The redshift of a galaxy, the amount by which the wavelengths of its light have been stretched during the journey to us, is in some ways the most fundamental and least ambiguous observable in cosmology. The redshift does not depend on which distance concept you use. It is a direct measurement of how much the universe has expanded since the light was emitted. A galaxy with a redshift of 1 has its light wavelengths doubled by the expansion, meaning the universe has expanded by a factor of 2 since that light was emitted. A galaxy with a redshift of 10 has its light wavelengths increased by a factor of 11, meaning the universe has expanded by a factor of 11 since that light was emitted. The highest redshift galaxy ever observed, as of the time of this writing, has a redshift of approximately 14, meaning the universe was roughly 15 times smaller when that galaxy emitted the light we are now receiving. The redshift is clean and unambiguous. What it maps to in terms of distance is where the ambiguity enters. The current comoving distance to a galaxy with redshift 14, calculated using the best current values of the cosmological parameters, is approximately 32 billion light-years. This is the number that opened tonight's discussion, and we can now understand why it is larger than the age of the universe in light-years. The galaxy was close when it emitted the light, and it has been receding ever since, and today it is 32 billion light-years away. The expansion has carried it to a current distance that far exceeds the distance that light could have traveled in the time since the Big Bang, not because anything has moved faster than light through space, but because space itself has expanded. The observable universe, defined as the sphere centered on us within which any light emitted since the Big Bang has had time to reach us, has a comoving radius of approximately 46 billion light-years. This defines the cosmological horizon, also called the particle horizon, the boundary beyond which we have had no causal contact since the beginning of the universe. Objects beyond the particle horizon are, in the most literal physical sense, unreachable and unknowable with any instrument that relies on light or any other signal traveling at or below the speed of light. They exist, presumably, and the laws of physics presumably apply to them, but no signal from them has ever reached us, and no signal from us has ever reached them. They are outside our observable universe, not because they are far away in the ordinary sense, but because the expansion of space has placed them beyond the causal reach of any signal since the Big Bang. The particle horizon is not the only horizon relevant to the concept of distance in the expanding universe. There is also the event horizon, distinct from the black hole event horizon we discussed in the previous video, which is the cosmological boundary beyond which events occurring today will never be observable to us in the future. Because the expansion of the universe is accelerating, there is a maximum distance from which light emitted today can ever reach us. Galaxies beyond this event horizon are already receding so fast that light they emit right now will never close the gap. The space between them and the photon will always be expanding faster than the photon can travel. The cosmological event horizon is currently at approximately 16 billion light-years. Galaxies beyond 16 billion light-years are currently receding so fast that any signal they send now will never reach us. The existence of the event horizon means that the observable universe is not just limited by the age of the universe and the time light has had to travel. It is also limited by the future. There are galaxies we can currently see, galaxies within our particle horizon, from which we will eventually be unable to receive any further information, as the accelerating expansion carries them beyond our event horizon. These galaxies will not disappear from our sky suddenly. They will gradually redshift and dim, their light becoming more and more stretched and their signal more and more attenuated, until they fade below any possible detection threshold. The process takes billions of years, but it is happening. The observable universe is shrinking in the sense that the number of galaxies from which we can receive new information is decreasing over time, as the accelerating expansion carries more and more of them past the event horizon. This progressive disappearance of galaxies beyond the event horizon has a specific implication for the long-term future of intelligent life, if it exists in the universe. The farther future beings look, the less they will see. The 2 trillion galaxies visible in today's observable universe will be reduced over time as expansion carries more and more of them past the event horizon. In 1 trillion years, if the current expansion continues, only the few dozen galaxies of the local group, those gravitationally bound to us, will remain accessible. Everything else will have receded past the event horizon and faded from the observable sky. A civilization in that far future, looking out at what appears to be an almost empty universe with only a few dozen galaxies visible, will have no observational evidence that the rest of the universe exists. They will have no way to know, from observation alone, that billions of other galaxies once shone within their cosmological horizon. The expanding universe will have erased the evidence of its own history. We are fortunate to be living in the era when the full extent of the universe is still visible. The 2 trillion galaxies of the observable universe are here, their light reaching us, their existence confirmable by current technology. The cosmic microwave background, the light of the early universe when it was only 380,000 years old, is still visible as a uniform glow in every direction, a relic of the hot, dense epoch before the first stars formed. The large-scale structure of the cosmic web, the filaments and voids and superclusters that took billions of years to assemble from the nearly uniform initial conditions of the Big Bang, is mapped in enough detail to reveal its statistical properties and constrain the cosmological parameters. All of this information is available to us in this particular era of cosmic history. None of it will be available to observers in the far future, who will find themselves apparently alone in a nearly empty universe. The information available to us today, in the overlap between the particle horizon and the current epoch of cosmic history, is the foundation for everything we know about the structure and extent of the universe. And that information, correctly interpreted, shows us a universe in which the ordinary concept of distance has been replaced by a family of related but distinct concepts, each appropriate for different questions, none of them quite matching the intuitive notion of distance as a stable, unambiguous spatial interval between 2 objects in a fixed world. The replacement of the ordinary concept of distance is not merely a technical inconvenience. It reflects something profound about the nature of the universe. The universe is not a static arena in which things exist at fixed distances from each other. It is a dynamic geometry, evolving over time, expanding at a rate that depends on its energy content, with a history that determines the mapping between the signals we receive and the properties of their sources. Distance in such a universe is not a simple measurement of spatial extent. It is an inference from observables, an inference that requires knowing the expansion history of the universe, the properties of the cosmological model, and the specific definition of distance being used. The universe has made distance complicated, not arbitrarily, but as a necessary consequence of its own dynamic geometry. Understanding this complication is not just a matter of getting the numbers right. It is a matter of understanding what the universe actually is, at the level of its large-scale structure and geometry. The universe is not a box of fixed size with things in it. It is a space-time geometry, four-dimensional, dynamic, governed by the Einstein field equations, with a specific history that began at the Big Bang and a specific future determined by the energy content. The distances we measure are not properties of the things we observe. They are properties of the space-time geometry between us and them, and that geometry is evolving. This is what makes the word distance stop making sense at cosmic scales. Not that distance becomes meaningless, but that the single word distance, which was adequate for all ordinary purposes, turns out to be carrying too much ambiguity when applied to a universe that is expanding, that has been expanding at different rates at different times, and in which the speed of light means that every observation is an observation of the past rather than the present. The universe is so big and so dynamic and so geometrically complex that the word distance has to be replaced by a family of related concepts, each precise and well-defined, none of them quite the same as what you meant when you used the word in ordinary experience. We have been building the conceptual foundation for the rest of tonight, establishing why the concept of distance requires care and qualification at cosmic scales. What we have not yet done is taken the full measure of what those cosmic scales actually are, not just in terms of numbers, but in terms of what those numbers mean for the structure of the universe, the distribution of matter and light within it, and the question of what lies beyond the boundaries that our instruments and our causal reach define. The observable universe is 46 billion light-years in comoving radius and contains 2 trillion galaxies. The universe beyond the observable is unknown, but presumably extends far further, possibly infinitely far. What we can say about the extent of the universe beyond our horizon, and what the observable universe tells us about the properties of the larger whole, is what we are going to explore next, because it is there that the concept of distance stops making sense in an even more fundamental way than the ambiguity of the expansion has produced. The history of how we learn the scale of the universe is one of the most extraordinary intellectual journeys in the history of science, and it is worth telling not just as a narrative of discovery, but as a lesson in how profoundly wrong our intuitions about scale can be, and how the correction of those intuitions, each time it has happened, has required a complete reorganization of the picture of where we are and what we are embedded in. The story is not a smooth progression from ignorance to knowledge. It is a series of discontinuous jumps, each one revealing that the universe is far larger than the previous picture allowed, each one making the previous picture look parochial in retrospect. We are almost certainly not at the end of this process. For most of human history, the scale of the universe was bounded by what the unaided eye could resolve. The stars were points of light at an unspecified distance, possibly all at the same distance on the surface of a celestial sphere surrounding the Earth, possibly at varying distances, but with no reliable method to determine which. The ancient Greeks debated the question of stellar distances, and some of them, including Aristarchus of Samos, proposed that the stars must be very far away to account for the absence of observed parallax as the Earth moved through space. Aristarchus proposed a heliocentric solar system in the 3rd century BCE, and he understood that if the Earth orbited the Sun, the nearby stars should shift slightly in apparent position relative to the distant background as the Earth moved around its orbit. The fact that no such shift was observed led most Greek astronomers to reject the heliocentric model, not because the physics was wrong, but because they underestimated the distances to the stars. The stars are so far away that the parallax is too small to detect with the naked eye. It took until 1838, when Friedrich Bessel measured the parallax of the star 61 Cygni, to produce the first reliable stellar distance measurement, confirming that even the nearest stars are at distances measured in light years. Before Bessel's measurement, the question of stellar distances was essentially unanswered. After it, the scale of the nearest stellar neighborhood was established, and subsequent parallax measurements rapidly extended the known distances to dozens and then hundreds of nearby stars. But the question of the overall size of the Milky Way, and of whether the nebulae visible in telescopes were objects within the Milky Way or entirely separate systems comparable to it, remained open well into the 20th century. The great debate between Harlow Shapley and Heber Curtis in 1920 crystallized the question. Shapley argued that the Milky Way was large, spanning roughly 100,000 light-years, and that the spiral nebulae visible in telescopes were small objects within or near the Milky Way. Curtis argued that the Milky Way was smaller, and that the spiral nebulae were island universes, galaxies comparable to the Milky Way but enormously distant. Both were partly right and partly wrong. Shapley was approximately correct about the size of the Milky Way. Curtis was approximately correct about the nature of the spiral nebulae. The resolution of the debate came from Edwin Hubble's observations at the Mount Wilson Observatory in 1923 and 1924, when he identified Cepheid variable stars in the Andromeda Nebula and used their period luminosity relationship to measure its distance. Hubble's distance to Andromeda, approximately 900,000 light-years in his initial calculation, was an underestimate due to errors in the Cepheid calibration that were not corrected until the 1950s. The correct distance is about 2.5 million light-years. But even the underestimate was sufficient to establish that Andromeda was not within the Milky Way, not a small nebula in the local stellar neighborhood, but a separate and enormous system of stars at a distance that placed it far beyond any possible interpretation as a local object. The universe had just expanded, discontinuously and dramatically, from the scale of the Milky Way to a scale that included at least one other comparable galaxy at millions of light-years distance. The Milky Way, which had seemed to be the universe, was revealed to be one galaxy among others. Hubble then turned his attention to the recession velocities of galaxies. Vesto Slipher had been measuring the spectra of spiral nebulae since 1912, and had found that most of them showed redshifted spectral lines, indicating recession from the Earth at velocities of hundreds to thousands of kilometers per second. This was puzzling when the nebulae were thought to be local objects within or near the Milky Way, since nothing in the local neighborhood was known to be moving at such speeds. When Hubble established the extragalactic distances, the recession velocities became even more puzzling. Hubble combined his distance measurements for a sample of galaxies with Slipher's velocity measurements and found a relationship. The more distant a galaxy, the faster it was receding. In 1929, he published this relationship, now called the Hubble Law, and it immediately suggested that the universe was expanding. The more distant galaxies were receding faster because all of space was expanding, and objects farther away were being carried along by the expansion at a proportionally greater rate. The Hubble law was not immediately interpreted as evidence for the expansion of space itself. For several years, it was discussed in terms of galaxies moving through space, as if the universe were a static arena in which galaxies happen to be flying apart. The correct interpretation, in which it is space itself that is expanding, and the galaxies are carried along rather than moving through the space, came from the theoretical work of Georges Lemaitre, a Belgian priest and physicist who in 1927 had independently derived the expanding universe solution from Einstein's general relativity, and had proposed that the recession of galaxies was evidence for this expansion. Lemaitre also noted that if the universe was expanding, Running time backward would imply that it had once been much smaller and denser, a primordial state he called the cosmic egg, which was later renamed the Big Bang. Einstein himself had resisted the expanding universe interpretation. In 1917, he had introduced the cosmological constant into his field equations specifically to produce a static universe, because a universe that was not static seemed physically implausible to him, and conflicted with the assumption of an eternal, unchanging cosmos that had been the default picture in Western science since antiquity. When Hubble's observations established the expansion, Einstein reportedly called the cosmological constant his greatest blunder, though the story may be apocryphal in its details. What is certain is that the discovery of the expansion demolished the assumption of a static eternal universe and replaced it with a dynamic, evolving cosmos with a specific beginning. The next great expansion of the known scale came from the discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson, two engineers at Bell Telephone Laboratories who were testing a microwave antenna and found a persistent noise in their instrument that came from all directions equally and could not be attributed to any known local source. The noise corresponded to a thermal spectrum at a temperature of approximately 2.7 degrees Kelvin, matching the prediction made by Ralph Alpher and Robert Herman in 1948, and elaborated by Robert Dicke and his colleagues, that the hot, dense early universe would have left a relic thermal radiation field that would be detectable today, cooled by the expansion to microwave wavelengths. The discovery of the CMB established the Big Bang model of cosmology on firm observational ground. The CMB is the oldest light in the universe, emitted when the universe was 380,000 years old, and the plasma of the early universe cooled enough to become transparent. It comes from a spherical shell of emission surrounding us in all directions, a shell whose current proper distance from us is approximately 46 billion light-years, the radius of the observable universe. Every observation of the CMB is an observation of the universe, as it was at this specific early time, seen from a vantage point inside the sphere of emission, with the oldest light in the observable universe arriving from every direction simultaneously. The CMB is not just evidence for the Big Bang. It is a detailed map of the initial conditions of the universe, encoded in the tiny temperature fluctuations across the sky. The temperature of the CMB is not perfectly uniform. It varies from place to place by about 1 part in 100,000, with hotter and cooler spots at specific angular scales that are determined by the physics of the early universe. These temperature fluctuations are the seeds of all subsequent structure. The slightly denser regions of the early universe, where the temperature was slightly higher because more matter was present, collapsed under gravity over the following billions of years to form the filaments and clusters of the cosmic web. The slightly less dense regions became the voids. The specific pattern of temperature fluctuations in the CMB, the statistical distribution of hot and cold spots at different angular scales, encodes information about the density of ordinary matter, and dark energy, the geometry of the universe, the expansion rate, and the nature of the initial density perturbations. The initial density perturbations that appear in the CMB are believed to be of quantum mechanical origin, produced by quantum fluctuations in the inflated field during the period of exponential expansion called inflation in the very early universe. Inflation stretched these microscopic quantum fluctuations to macroscopic scales, imprinting them on the distribution of matter and energy throughout the universe. The specific statistical properties of the temperature fluctuations in the CMB, their near-Gaussian distribution, their near-scale invariant power spectrum, their specific pattern of acoustic peaks and troughs in the angular power spectrum, all match the predictions of the inflationary model with extraordinary precision. The acoustic peaks in the CMB power spectrum deserve special attention because they reveal the distant scale of the universe in a very direct way. The temperature fluctuations in the CMB are not random. They have a preferred scale, a specific angular size on the sky that corresponds to the distance that sound waves in the early universe plasma could travel before the plasma became transparent, and the sound waves froze in place. This distance is called the sound horizon, and it is a standard ruler, a length that can be calculated from first principles using the known physics of the early universe plasma. By measuring the apparent angular size of the acoustic peaks in the CMB, which corresponds to the apparent angular size of the sound horizon at the distance of the last scattering surface, and comparing it to the known physical length of the sound horizon, cosmologists can calculate the distance to the last scattering surface, and hence the geometry and expansion history of the universe. This standard ruler argument, using the acoustic oscillations in the CMB, is one of the most powerful distance measurement techniques in cosmology. It is independent of the Cepheid distance ladder and gives a completely different kind of measurement of the universe's geometry and expansion rate. The agreement between the CMB-based distance scale and the supernova-based distance scale, at the level of a few percent, is one of the strongest confirmations of the standard cosmological model. The disagreement between the CMB-based Hubble constant and the local distance ladder Hubble constant, the Hubble tension, is the one place where the two approaches diverge, and it is the signal that something may be incomplete in the current picture. The acoustic oscillations are not just visible in the CMB. They are also imprinted in the distribution of galaxies, where they appear as a preferred clustering scale called the baryon acoustic oscillation scale. At a separation of roughly 500 million light-years, galaxies are slightly more likely to be clustered together than at other separations, because this distance corresponds to the sound horizon of the early universe. Measuring this clustering scale in galaxy surveys provides a standard ruler at low redshift that complements the CMB standard ruler at high redshift, and the two together constrain the expansion history of the universe across a wide range of cosmic time. The large-scale surveys that have mapped the baryon acoustic oscillation scale, including the Sloan Digital Sky Survey and its successors, have measured the positions and redshifts of millions to tens of millions of galaxies, and produced the most detailed three-dimensional maps of the large-scale structure of the universe ever made. These maps reveal the cosmic web of filaments and voids in exquisite detail, confirming the predictions of the standard cosmological model for the growth of structure under gravity. They also confirm the flatness of the universe's geometry, the presence of dark energy, and the specific values of the cosmological parameters at a level of precision that has transformed cosmology from a qualitative science into a precision measurement discipline. The precision of modern cosmology is worth pausing on because it represents a genuinely remarkable achievement. The age of the universe is known to within about 1%. The fraction of the universe's energy density in ordinary matter, dark matter, and dark energy is known to within a few percent. The geometry of the universe is known to be flat to within the measurement uncertainties. The amplitude and spectral index of the primordial density perturbations are known to within fractions of a percent. These parameters, taken together, constitute the standard model of cosmology, the lambda CDM model, and they have been confirmed by multiple independent measurements using completely different observational techniques. The standard model of cosmology is one of the most precisely tested theories in all of science. And yet the precision of the cosmological parameters does not resolve the conceptual difficulty we identified at the beginning of tonight, the fragmentation of the concept of distance. The precise knowledge of the cosmological parameters allows us to calculate the different distance measures to any given object with high accuracy, given its redshift. But having a precise number for each of the four distance measures does not eliminate the ambiguity. It quantifies the ambiguity. We now know precisely how different the four distance measures are for any given object, and the differences are large enough that specifying which distance you mean is always necessary for distant objects, and sometimes even for moderately distant ones. What the precision of modern cosmology does give us is the ability to trace the history of the expansion with high accuracy, to reconstruct the scale of the universe at any past epoch from the current measurements, and to predict the scale of the universe at any future epoch under the assumption that the current dark energy model is correct. This history of the expansion, the function that relates the scale factor of the universe to cosmic time, is called the Friedmann equation solution for our specific combination of cosmological parameters, and it is what underlies all of the distance calculations we have discussed. The Friedmann equation is the dynamical equation of cosmology, derived from Einstein's general relativity applied to a homogeneous and isotropic universe. It relates the expansion rate, described by the Hubble parameter, which is the time derivative of the scale factor divided by the scale factor, to the total energy density of the universe, which includes contributions from ordinary matter, dark matter, radiation, and dark energy. The behavior of the expansion is different depending on which component dominates the energy density at any given time. In the radiation-dominated era, the first few thousand years after the Big Bang, the energy density was dominated by the photons and neutrinos of the hot early plasma. The expansion rate in this era was proportional to the inverse square root of time, meaning the universe was expanding rapidly but decelerating. In the matter-dominated era, from a few thousand years after the Big Bang until about 5 billion years ago, the energy density was dominated by ordinary matter and dark matter. The expansion rate in this era was proportional to the inverse 2/3 power of time, meaning the universe was still expanding, but decelerating more slowly than in the radiation era. In the dark energy-dominated era that began about 5 billion years ago, the energy density is dominated by the cosmological constant, and the expansion rate is accelerating exponentially. The transition from deceleration to acceleration happened at a specific redshift, approximately 0.7, about 5 to 6 billion years ago. These three eras of expansion history are what produce the specific values of the four distance measures for any given object. The history of the expansion determines how much the universe has stretched between the time of emission of a photon and the time of its reception, and this stretching determines the redshift, the proper distance, the luminosity distance, and the angular diameter distance in a specific way that depends on the relative contributions of matter, radiation, and dark energy to the expansion at each epoch. The transition from deceleration to acceleration is particularly important for understanding why the concept of distance has become so ambiguous for distant objects. During the deceleration era, the expansion was slowing down, and photons emitted from distant objects had an easier time overcoming the expansion to reach us, because the expansion rate was decreasing over time. During the acceleration era, the expansion is speeding up, and photons emitted from beyond the cosmic event horizon will never reach us regardless of how long we wait. The transition between these two regimes happened roughly 5 billion years ago, which is close enough to the current epoch that it has a significant effect on the distance to objects at redshifts of order 1. The objects in the redshift range where the supernova observations that discovered the acceleration are most sensitive. The discovery of the accelerating expansion in 1998, using Type Ia supernovae as standard candles, is one of the most significant scientific discoveries of the late 20th century. Two independent teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were measuring the distances to supernovae at redshifts of about 0.5 to 1, using the luminosity distance, and comparing them to the distances predicted by cosmological models with different amounts of matter and dark energy. If the universe contained only matter, the expansion should have been decelerating, and the distant supernovae should have been closer than the Hubble flow alone would predict. Instead, the The supernovae were farther away than predicted. The expansion was not decelerating. It was accelerating. The universe contained a dark energy component, with a density that was acting as a repulsive term in the Friedmann equation and causing the expansion to speed up rather than slow down. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. The accelerating expansion has been confirmed by multiple subsequent observations using different techniques, including the CMB, the baryon acoustic oscillations, and later supernova samples at higher redshifts. The dark energy that drives the acceleration constitutes approximately 68% of the total energy density of the universe, and its nature remains one of the central unsolved problems of physics, as we discussed in the expiration date video. For the concept of distance, the accelerating expansion has a specific consequence that is worth stating explicitly. The acceleration means that the cosmic event horizon is not growing in comoving coordinates. Objects that are currently beyond the event horizon will never enter it. Objects that are currently within the event horizon but near its edge will eventually cross it and disappear from our observable universe. The observable universe is losing territory at an accelerating rate, as more and more galaxies recede past the event horizon, and their light can no longer catch up to us. In the far future, the only galaxies within our event horizon will be those in the local group, the gravitationally bound cluster of galaxies that includes the Milky Way and Andromeda, and a few dozen smaller companions. Everything else, the 2 trillion galaxies currently visible, will have receded past the horizon and disappeared, leaving observers in the far future with a universe that appears to consist of a single galaxy in an otherwise empty void. This is one of the most profound implications of the accelerating expansion for the concept of distance. The scale of the observable universe is not fixed. It is shrinking, in the sense that the number of galaxies within our causal reach is decreasing over time as the acceleration carries more and more of them past the event horizon. The 46 billion light-year radius of the observable universe is the radius as of now, at this specific moment in cosmic history. In 100 billion years, the observable universe in terms of number of accessible galaxies will be much smaller, reduced to the local group. The concept of the observable universe and the distances we assign to things within it are time-dependent in a way that reflects the dynamics of the expansion. The specific scale of the observable universe, the reason it is 46 billion light-years in radius rather than some other number, reflects the specific age of the universe and the specific expansion history. If the universe were twice as old, the observable radius would be larger. If dark energy had been stronger, the event horizon would have closed off earlier and the observable universe would be smaller. The scale we observe is a snapshot of the universe at a specific moment in its evolution, determined by the interplay of the initial conditions at the Big Bang, the subsequent expansion history, and the specific values of the cosmological parameters that our measurements have established. Understanding this helps to demystify what might otherwise seem like a remarkable coincidence, that the observable universe has a radius of 46 billion light-years, while the age of the universe is only 13.8 billion years, a factor of more than 3 between the two numbers. This is not a coincidence. It is a specific consequence of the expansion history. The universe was expanding faster in the past, when matter and radiation dominated the energy density, and the Hubble parameter was larger, and photons that were emitted when the universe was young could cover much greater proper distances in the early high expansion rate era than they could cover in the current low expansion rate era. The comoving distance to the last scattering surface, the boundary of the observable universe, reflects the integrated expansion of the universe over its entire history, weighted by the expansion rate at each epoch. The expansion rate at the moment of decoupling, when the CMB was emitted, was enormously larger than it is today. The Hubble parameter at decoupling was approximately 60,000 times larger than today's value. A photon emitted at decoupling was in a universe that was expanding 60,000 times faster than today, and the space it was moving through was being stretched at a rate that would have seemed impossibly fast by today's standards. As the universe expanded and cooled and the matter density dropped, the expansion rate decreased, and the rate at which photons could cover proper distance decreased as well. The 46 billion light-year radius is the cumulative result of 13.8 billion years of photon travel through a universe whose expansion rate was much faster in the early stages and has been gradually slowing until about 5 billion years ago, when the dark energy took over and started accelerating it again. The James Webb Space Telescope, which began science operations in 2022, has pushed the boundary of our observations of the early universe to redshifts higher than any previous instrument could reach with detailed spectroscopic confirmation. The telescope has confirmed galaxies at redshifts of 12 and higher, corresponding to epochs when the universe was less than 400 million years old, less than 3% of its current age. These galaxies are among the first structures that formed after the Big Bang, and their properties, their sizes, their stellar masses, their star formation rates, are providing observational constraints on the earliest phase of galaxy formation that were previously inaccessible. Some of the early results from the James Webb have been surprising. Several galaxies at high redshift appear to be more massive and more evolved than the standard model of galaxy formation predicts for such early cosmic times. The standard model assumes that galaxies build up their stellar mass gradually over billions of years, with the most massive galaxies forming last through the hierarchical merging of smaller systems. The massive early galaxies found by the James Webb challenge this picture, suggesting that either the standard model of galaxy formation is incomplete, or that the cosmological parameters are slightly different from their current best values, or that there is some physical process in the early universe, perhaps more efficient star formation or a different dark matter model, that allowed massive galaxies to form faster than the standard model predicts. These early James Webb results are still being analyzed and debated, and the interpretation of the high redshift galaxy masses requires careful handling of the systematic uncertainties in the spectral energy distribution modeling used to infer stellar masses from observed fluxes. But even taking the uncertainties into account, there is a tension between some of the James Webb observations and the predictions of the standard model that is being taken seriously by the theoretical community. It may be the harbinger of new physics in galaxy formation, or it may be resolved by better modeling of the known physics. The resolution will come from more observations, more detailed spectroscopy, and more careful comparison with simulations, and the James Webb will be central to that effort over the next decade. The Euclid Space Telescope, launched in 2023, is conducting a wide-area survey of galaxy shapes and positions that will map the large-scale structure of the universe over a substantial fraction of the sky, and to redshifts of up to about 2. Euclid's primary scientific goals are the measurement of the dark energy equation of state and the growth rate of structure, using weak gravitational lensing and baryon acoustic oscillations as the primary probes. The combination of Euclid's large-area weak lensing and galaxy clustering data, with the deep spectroscopic surveys from the ground and the detailed high redshift observations from the James Webb, will provide a comprehensive picture of the large-scale structure of the universe from the earliest observable epochs to the present. The Square Kilometre Array, currently under construction in South Africa and Australia, will when complete be the largest radio telescope in the world by a large margin, with a total collecting area of approximately 1 square kilometer distributed over thousands of individual antenna stations. The SCA will observe the universe in radio wavelengths with sensitivity and angular resolution far exceeding any previous radio telescope. Its scientific goals span a wide range from the detection of pulsars and transient events to the mapping of neutral hydrogen across the universe. The mapping of neutral hydrogen through the 21-centimeter emission line of atomic hydrogen is particularly relevant for the concept of cosmological distance because it will allow the three-dimensional mapping of the distribution of matter in the universe at redshifts where optical surveys are limited by the faintness of galaxies. The SKA's hydrogen maps will trace the large-scale structure of the universe to redshifts of several, providing a complementary probe of the expansion history and the growth of structure to the optical and infrared surveys. The combination of all these observational programs, the James Webb mapping the earliest galaxies, Euclid mapping the large-scale structure at intermediate redshifts, the SKA mapping the hydrogen distribution from low to high redshift, the Roman Space Telescope measuring dark energy through supernovae and weak lensing, the Daisy spectrograph measuring baryon acoustic oscillations in millions of galaxy spectra, and the Vera Rubin Observatory conducting a decade-long photometric survey of the southern sky will produce a picture of the universe's large-scale structure and expansion history that is more detailed and more precise than anything currently available. The cosmological parameters will be measured with unprecedented precision. The Hubble tension will either be resolved or confirmed as a sign of new physics, and the nature of dark energy will be much better constrained. But none of these observations, however precise, will resolve the fundamental conceptual issue that opened tonight's discussion. The four distance measures will still exist, still give different numbers, still require specification of which one you mean. The cosmic event horizon will still be shrinking in terms of the number of galaxies within reach. The distinction between the observable universe and the universe beyond the horizon will still be absolute. The fragmentation of distance at cosmological scales is not a measurement problem that better instruments will solve. It is a feature of the physics of an expanding universe that will remain true regardless of how precise our measurements become. What better measurements do give us is a more detailed and more accurate version of the history encoded in the distances. The specific values of the four distance measures to any given object encode the entire expansion history of the universe between the time of emission and the time of observation. From the redshift and the luminosity distance of a supernova, you can reconstruct the expansion rate at the epoch when the light was emitted. From the pattern of acoustic peaks in the CMB, you can reconstruct the density of matter and energy at the time of decoupling. From the clustering of galaxies at the baryon acoustic oscillation scale, you can reconstruct the expansion history at intermediate redshifts. The distances, for all their ambiguity, are data. They encode the history of the universe in a way that can be decoded with sufficient measurements and sufficient theoretical modeling. This is the deepest way to think about what cosmological distances are measuring. They are not measuring the separation between objects in a static space. They are measuring the integrated history of the expansion of a dynamic space, the accumulated stretching of the metric between two events in spacetime separated in both space and time. The different distance measures are different integrals over this expansion history, weighted in different ways, corresponding to different physically meaningful quantities. The light travel distance is the integral of the speed of light over cosmic time. The proper distance is the integral of the speed of light over cosmic time, corrected for the expansion that occurred while the light was in transit. The luminosity distance is the proper distance multiplied by the square of 1 plus redshift, accounting for the energy and rate dilution of the photons. The angular diameter distance is the proper distance divided by 1 plus redshift, accounting for the size of the emitting region at the time of emission. In each case, the distance is telling you something specific about the relationship between two events in an expanding spacetime. The ambiguity is not ambiguity in the usual sense of uncertainty or imprecision. It is the inevitable result of trying to collapse a four-dimensional relationship, the relationship between two events in a spacetime with a specific expansion history, into a single number. There is no single number that captures all of the physically meaningful aspects of that four-dimensional relationship, And the four distance measures are four different ways of extracting different aspects of it. The universe, in this sense, is not too big for the concept of distance to apply. It is too big for any single concept of distance to capture everything that matters. The fragmentation of distance at cosmological scales is not a failure of the concept. It is the concept revealing the structure of the universe at the scales where the expansion can no longer be ignored. At those scales, the universe is telling us something that it cannot tell us at smaller scales. That space and time are not independent, that the distance between two things depends on when you measure it, and that the history of the universe is encoded in the light that crosses it. Space and time are not independent. The history of the expansion is encoded in the light that crosses it. Those two sentences, which close the previous part of tonight's discussion, point towards something that the concept of distance has been obscuring all along. The reason distance fragments at cosmological scales is not merely that the universe is large and expanding. It is that, in a universe described by general relativity, space and time are not separate things. They are aspects of a single four-dimensional structure called spacetime, and the separation between two events in spacetime cannot be cleanly divided into a spatial part and a temporal part in any observer-independent way. The fragmentation of distance at cosmological scales is the large-scale manifestation of a fact that is already true at all scales, that distance and time are not independent measurements, but aspects of a single spacetime interval whose decomposition into spatial and temporal parts depends on the observer. Special relativity established this in 1905. The speed of light is the same for all observers regardless of their motion, and this constancy of the speed of light requires that different observers in relative motion measure different distances and different time intervals between the same pair of events, with the differences being precisely such that the spacetime interval, the combination of spatial separation and temporal separation in a specific mathematical way, is the same for all observers. Two observers moving relative to each other will disagree about the distance between two events and about the time between those events, but they will agree about the spacetime interval. The interval is the objective quantity. The decomposition into space and time is observer-dependent. The consequence of this for cosmology is the absence of a well-defined universal now. At any given moment of your local experience, there is no well-defined sense in which some particular configuration of distant matter constitutes the universe as it is right now. The distant galaxy that you see in a telescope is not the galaxy as it is now. It is the galaxy as it was when the light you are receiving was emitted, which was billions of years ago. The question of what that galaxy is doing right now, at this moment in your local time, has no single answer in a relativistic universe. The answer depends on how you define simultaneity, which in turn depends on your state of motion, and in an expanding universe there is a natural choice of simultaneity, the one that makes the universe appear homogeneous and isotropic, but this is a convention, not an absolute fact. The conventional simultaneity of cosmology, the one used to define the proper distance and the comoving coordinates in which galaxies are at rest, is called cosmic time, or the comoving time coordinate. In this convention, the universe looks the same in all directions at any given moment of cosmic time, and the CMB has the same temperature everywhere in the sky when the light was emitted, and the density of matter and energy is uniform across space at any given cosmic time. This is the slicing of spacetime into space and time that makes the Friedmann equation work, that makes the expansion look like a uniform stretching of space rather than a motion of objects through space, and that underlies the definitions of the proper distance and the scale factor. But cosmic time is a convention. It is the most natural and most useful convention for describing the large-scale structure of the universe, but it is not the only possible one, and different conventions give different pictures of what is happening simultaneously at different locations. An observer moving at high velocity relative to the local Hubble flow would define simultaneity differently, and would assign different values of cosmic time to events at distant locations. The proper distance to a distant galaxy, defined as the distance at a fixed moment of cosmic time, would be different for this observer than for an observer at rest in the Hubble flow. This is not a problem to be solved. It is a reflection of the basic structure of relativity, in which simultaneity is observer-dependent. For practical cosmology, the cosmic time convention is so natural and so useful that it is essentially always used, and the proper distance is the most natural definition of distance in this convention. But it is worth keeping in mind that the proper distance is defined relative to a specific convention of simultaneity, and that the ambiguity of cosmological distance is not just a consequence of the expansion, but also a consequence of the relativity of simultaneity. The universe does not have a single answer to the question, what is happening right now at that distant galaxy? And the different distance measures are in part different ways of choosing an answer to this unanswerable question. The deepest way to visualize the causal structure of the entire universe, including the past, present, and future, is through a Penrose diagram, the same type of diagram we used in the black hole video to represent the causal structure of black hole spacetimes. A Penrose diagram of the universe represents the entire history of the universe, from the Big Bang to the far future, in a finite diagram that preserves the causal structure. In the Penrose diagram of our universe, the Big Bang appears as a horizontal line at the bottom of the diagram, the surface from which all of spacetime emerges. The far future, including the eventual heat death or whatever terminal state the universe reaches, appears as a horizontal line at the top. Our position in the universe, right now, tonight, appears as a point somewhere in the middle of the diagram, and the observable universe appears as the region of the diagram from which light can have reached our position since the Big Bang. In the Penrose diagram of our universe, the boundary of the observable universe, the surface of last scattering at redshift 1090 from which the CMB was emitted, appears as a surface of constant cosmic time at a specific height above the bottom of the diagram. The light cone from our current position, traced backward in time, intersects this surface at a circle whose size corresponds to the proper distance of roughly 46 billion light-years to the edge of the observable universe. Everything above and below, and to the sides of our backward light cone, is in our causal past, the region of spacetime that could in principle have influenced our current position. Everything outside our backward light cone, at the same cosmic time as our current position but at greater proper distances, is not in our causal past. It is the region of the universe that we cannot observe, not because the light has not reached us yet, but because we have not yet had time to receive the light from those events. The Penrose diagram makes vivid something that the ordinary spatial picture of the universe obscures. The Big Bang is not a point in space from which the universe expanded. It is a moment in time from which all of spacetime emerged. Every location in the universe originated at the Big Bang. The Big Bang did not happen at a specific place that is somewhere out there in space. It happened everywhere simultaneously, at the initial moment of cosmic time, and every point in the current universe is equally the result of the Big Bang. The CMB is coming from all directions not because we are near the center of an explosion, but because the surface of last scattering is a surface of constant cosmic time in the past, surrounding us in all directions equally because we are embedded in the middle of the spacetime that emerged from the Big Bang. This is one of the most frequently misunderstood aspects of the Big Bang, and the Penrose diagram is the cleanest way to see why the misunderstanding occurs. The ordinary picture of the Big Bang as an explosion from a point creates the false impression that the universe has a center, that there is a place where the Big Bang happened that is distinct from the places where the matter has since traveled to. In the Penrose diagram, there is no center. The Big Bang is the bottom edge of the diagram, a line, not a point, and every location in the universe today traces its origin to a point on that line. The universe is not expanding into anything. There is no outside into which it is expanding. The expansion is the stretching of the spacetime represented by the interior of the diagram, and there is nothing outside the diagram to expand into. The cosmic microwave background in the Penrose diagram is the wall of fire at the edge of what can be seen, the boundary between the observable and the unobservable, not in the spatial sense, but in the causal sense. Below the surface of last scattering in the early universe plasma, the universe was opaque to light. Photons could not travel freely. They were constantly being absorbed and re-emitted by the hot plasma, and no information from before the surface of last scattering can reach us in the form of electromagnetic radiation. The surface of last scattering is the edge of what we can see with light. It is the cosmological horizon in the temporal sense, the point beyond which the universe's history is invisible to electromagnetic observation. Before the surface of last scattering, the universe was not dark, but it was opaque. It was filled with hot, dense plasma that was in a state of thermal equilibrium, with radiation and matter locked together in a featureless thermal bath. The specific information about the distribution of matter in this pre-recombination universe is not encoded in the photons of the CMB because the frequent scatterings in the plasma erased the detailed history and replaced it with a thermal spectrum. What is preserved in the CMB is the distribution of matter at the moment of decoupling, the last scattering surface, encoded in the tiny temperature fluctuations that reflect the density variations at that epoch. The universe before the surface of last scattering is not completely inaccessible. The relic neutrinos from the first second after the Big Bang, the cosmic neutrino background, were produced when the universe was 1 second old and decoupled from ordinary matter at that time, much earlier than the photons. In principle, a detector sensitive enough to detect relic neutrinos could observe the universe as it was at 1 second of age, rather than 380,000 years. The Ptolemy experiment is attempting this. Similarly, gravitational waves produced in the very early universe, including those from inflation and from any phase transitions that occurred in the first fraction of a second, would have propagated freely since their production, and could in principle be detected, providing a window into the universe before the surface of last scattering. Future space-based gravitational wave detectors, including LISA and its successors, may be sensitive to gravitational waves from the inflationary epoch, opening a window into the universe at energies and epochs that are completely inaccessible to electromagnetic observation. The picture of the universe that emerges from all of these observational windows, electromagnetic and gravitational and neutrino, is a picture of a spacetime that is richer and more structured than the simple sphere of observable universe suggests. The observable universe is not a uniform ball of matter and radiation. It is a nested series of causal shells, each one revealing the universe at a different epoch. The galaxies at various redshifts revealing the universe from a few 100 million years ago to the present. The CMB revealing the universe at 380,000 years. The hypothetical neutrino background revealing the universe at 1 second. The hypothetical inflationary gravitational wave background revealing the universe at a fraction of a second. Each shell is a different temporal cross-section of the same spacetime, and together they provide a four-dimensional picture of the universe's history rather than a three-dimensional snapshot of its current state. The picture is incomplete in specific ways. The surface of last scattering is the earliest we can see with light, and the universe before that is invisible to electromagnetic observation. The cosmic event horizon is the latest we can see for any given epoch, and anything beyond it is permanently inaccessible. The portion of the universe beyond the observable sphere is statistically similar to what we observe but specifically different, with different configurations of matter and different histories, forever beyond reach. And the question of what the universe is like beyond our inflationary bubble, if other bubbles exist in the multiverse, is not just inaccessible but arguably undefined in any operational sense. What we can see is a sphere 14 gigaparsecs in radius containing 2 trillion galaxies arranged in a cosmic web, whose structure was seeded by quantum fluctuations in the first fraction of a second after the Big Bang. This is a specific, finite, observable portion of what may be an infinite or much larger universe. It is the universe as we can know it, bounded by the causal structure of spacetime and the age of the universe and the physics of the early plasma. It is extraordinarily large. It is incomprehensibly rich in structure, and it is a small fraction of what exists. The question of how a mind embedded in this space makes sense of its dimensions is one that has a surprising answer. The answer is, with great difficulty and only recently. For most of human history, the universe was conceptually small. The Earth was the center. The stars were lights on a celestial sphere a few tens of millions of kilometers away. The total spatial extent of the universe was comparable to the distance from the Earth to the Sun, a number that the Greeks had estimated to be around a few million kilometers, orders of magnitude smaller than the actual distance. The jump from this picture to the modern cosmological picture happened over the course of about 400 years, from Copernicus and Galileo through Newton and Herschel through Hubble and Penzias and Wilson to the current generation of precision cosmology. Each step in this expansion of the known universe required a reorganization of the human self-concept, a shift in the answer to the question, where are we? When the Earth was the center of the universe, the answer was, we are at the center of everything. When Copernicus moved the center to the Sun, the answer became, we are at the center of the solar system, which is at the center of the universe. When Herschel mapped the distribution of stars in the Milky Way and found the Sun to be roughly in the center, the answer was, we are near the center of the galaxy, which is the universe. When Shapley moved the Sun from the center to the outer disk of the Milky Way, the answer became, we are in the outer part of the galaxy, which is the universe. When Hubble showed that the Milky Way was one of many galaxies, the answer became, we are in one of many galaxies and there is no center. When the CMB established the expanding universe and its Big Bang origin, the answer became, we are at an arbitrary location in a universe that began 13.8 billion years ago and has been expanding ever since, and the concept of center does not apply. At each step, the universe got larger and our position became less special, less central, less obviously significant in the spatial sense. This is sometimes presented as a story of progressive humiliation, the Copernican principle operating repeatedly to remove humans from the center of things. But this framing misses something important. The universe getting larger did not make our position less significant. It made it more specifically located. We are not at the center of the observable universe in any privileged sense, but we are at a specific location in a specific galaxy, in a specific supercluster, in a specific cosmic web, at a specific moment in the history of a universe, whose expansion history we understand with remarkable precision. The location is specific. The knowledge of the location is specific. And the knowledge itself, the ability to measure the angular diameter distance to the CMB and derive from it the geometry of the universe, the ability to detect the baryon acoustic oscillation scale in galaxy surveys and use it to constrain the expansion history, the ability to identify quantum fluctuations from the inflationary epoch in the pattern of temperature variations across the microwave sky, is one of the most extraordinary things that has happened in the 14 billion year history of this universe. The specific problem of trying to picture the universe as a whole, to hold the full spatial extent of the observable sphere in mind simultaneously, is one that even professional cosmologists admit is not really possible in any intuitive sense. The numbers are large enough that the mind cannot form a genuine image of them. The 46 billion light-year radius of the observable universe cannot be pictured in the way that you can picture the distance from your house to the nearest city. The 2 trillion galaxies cannot be imagined as individual objects the way you can imagine 2 trillion of anything else. The scale hierarchy from the meter of the human body to the gigaparsec of the observable universe spans 30 orders of magnitude, a factor of 10 to the 30th, and no single act of imagination can hold that range. What can be held, and what is actually useful for understanding the universe, is not a picture but a set of relationships. The relationship between the size of a planet and the size of a star, and the size of a galaxy and the size of the observable universe. The relationship between the four distance measures and what each one tells you about the object you are observing. The relationship between the redshift of a distant galaxy and the epoch at which its light was emitted, and the state of the universe at that epoch. The relationship between the temperature fluctuations in the CMB and the acoustic oscillations, and the density perturbations and the large-scale structure. These relationships can be understood precisely and rigorously, even if the scales themselves cannot be intuitively grasped. The inability to intuitively grasp the scale of the universe is not a failure of human cognition. It is a consequence of the fact that the scale of the universe vastly exceeds the scale at which human cognition evolved. Our intuitions about distance were calibrated by natural selection for the distances relevant to survival on the surface of a planet, distances from centimeters to perhaps hundreds of kilometers. The cognitive machinery that handles these distances, the visual system, the sense of depth and scale, the ability to estimate how far away a prey animal or a predator is, was sufficient for the environment in which it evolved. It was not calibrated for distances measured in megaparsecs, and there is no reason to expect it to work well at those scales. What works instead is mathematics. The equations of cosmology, the Friedmann equation and the geodesic equations and the transfer function of the CMB, work at all scales equally well. They do not care that the numbers they produce are too large for intuitive comprehension. They produce precise predictions for the temperature fluctuations in the CMB at specific angular scales. And those predictions can be compared to observations with a precision of better than 1%. The distance to a supernova at redshift 1 can be calculated from the cosmological parameters and compared to the observed luminosity with a precision sufficient to detect the difference between an accelerating and a decelerating universe. The mathematics compensates for the inadequacy of intuition at cosmological scales. The history of science is in large part the history of developing mathematical tools that extend human cognition beyond its evolved limits. Calculus extended the cognitive ability to handle continuously changing quantities. Probability theory extended the cognitive ability to reason about uncertain outcomes. Statistical mechanics extended the cognitive ability to handle the collective behavior of enormous numbers of particles. And cosmology, with its Friedmann equations and its conformal diagrams and its power spectra and its transfer functions, extends the cognitive ability to handle distances and timescales and matter densities that are completely beyond the reach of unaided intuition. The specific extension that cosmology represents is the ability to hold the entire history of the universe in a single mathematical framework, and to extract from that framework precise quantitative predictions that can be compared to observations. The Penrose diagram of the universe, which compresses the entire history from the Big Bang to the far future into a finite diagram while preserving the causal structure, is a mathematical representation that allows the causal relationships between different parts of the universe's history to be seen at a glance. The Friedmann equation, which relates the expansion rate to the energy density at any moment, is a mathematical compression of the universe's dynamics that allows the entire expansion history to be computed from the current values of the cosmological parameters. These mathematical representations are not mere tools for calculation. They are the way that human minds genuinely know the universe at scales that intuition cannot reach. There is a specific quality of knowledge that comes from understanding the universe at these scales, a quality that is different from the knowledge of the familiar world. It is the knowledge of relationships rather than things, of patterns rather than objects, of the structure of the possible, rather than the contingency of the actual. When you understand that the angular diameter distance has a maximum at redshift 1.6, you are not just memorizing a fact about a specific number. You are understanding a structural feature of the geometry of an expanding spacetime, a feature that would be true in any universe with the same basic cosmological model, regardless of the specific values of the parameters. When you understand that the proper distance to a distant galaxy is greater than the light-traveled distance by a factor that depends on the expansion history between emission and observation, you are understanding the relationship between the geometry of spacetime and the propagation of light, a relationship that is a consequence of the general theory of relativity and is true in any universe described by that theory. This kind of structural knowledge is what science offers at scales beyond the reach of intuition, and it is genuinely useful for understanding the universe, even when the specific numbers cannot be held in the mind. You do not need to be able to picture 46 billion light-years to understand why the observable universe has that specific radius rather than some other. You need to understand the relationship between the age of the universe, the expansion history, and the distance that light can travel in an expanding spacetime. The number follows from the relationship, and the relationship is something that can be genuinely understood. The same is true for the fragmentation of distance that we have been discussing all night. You do not need to be able to intuitively grasp the difference between 13.4 billion light-years and 32 billion light-years and 160 billion light-years as three distances to the same galaxy. You need to understand what each of those numbers is measuring, why they differ, and what each one tells you about the galaxy and about the universe. The fragmentation is not confusion. It is precision, the precise articulation of different aspects of the four-dimensional relationship between two events in an expanding spacetime. The universe is not too big for the concept of distance. It is too big for a single concept of distance. And the multiple concepts that replace the single concept are not a failure of precision, but an increase in it. We have more information about the relationship between two events in the universe when we know all four distance measures than when we know only one. The universe, by requiring us to replace the single intuitive concept of distance with a family of mathematically precise concepts, has forced a more accurate description of what distance actually is in a universe where space itself has a history. Sitting with this, in the quiet of the night, in the specific moment of the stelliferous era that is tonight, produces a specific kind of clarity. The night sky is not a flat surface of lights at varying distances. It is a four-dimensional object, a spacetime map, with photons arriving from different proper distances and different luminosity distances, and different angular diameter distances, and different light travel distances, all arriving simultaneously at your location after traveling through an expanding space for varying fractions of the universe's age. The stars in the Milky Way whose light left them a few hundred years ago. The Andromeda Galaxy whose light left it 2.5 million years ago. The Virgo cluster whose light left it 53 million years ago. The most distant quasars whose light left them 12 billion years ago. And the CMB, whose photons left the surface of last scattering 380,000 years after the Big Bang, and have been traveling through the expanding space for 13.4 billion years to arrive at your location tonight. All of this is happening simultaneously, right now, in the specific moment that is tonight. Every photon arriving at your eye or your telescope is a message from a different epoch of the universe's history, and the collection of messages arriving from all directions simultaneously is a four-dimensional picture of the universe's history, not a two-dimensional image of its current state. The night sky is an archive, not a snapshot. It is the universe's record of its own past, delivered to your location by the physics of light propagation through an expanding spacetime. And the concept of distance is the tool we use to read the archive, to translate the arrival time of each photon into the epoch from which it was sent, and the location from which it was sent, and the state of the universe at that epoch. The tool is imprecise when used carelessly, because distance means four different things in cosmology, and using the wrong one produces a wrong picture. But the tool is exquisitely precise when used correctly, when the right distance measure is chosen for the right purpose, and the relationships between the different measures are understood. The universe rewards this precision. It reveals its history to those who ask the right questions in the right language, and the language of cosmological distances, for all its complexity and all its fragmentation, is the right language for asking questions about a universe that has been expanding since its first moment. The universe rewards precision. That sentence carries more weight than it first appears, because it connects the mathematical tools we have been discussing to something that is not primarily about mathematics. The universe rewards precision in the sense that asking the right question in the right language reveals the universe's history. But there is another sense in which the universe rewards precision, a more literal and more astonishing sense. The universe is precisely the size it needs to be for anything to exist in it that is capable of measuring its size. This is not a coincidence in any trivial sense. It is a relationship between the scale of the universe and the conditions required for the emergence of complexity. And tracing that relationship reveals something about why the universe is as large as it is and why we are here to notice. Begin with a question that looks like it has an obvious answer. Why is the universe so large? The observable universe contains 2 trillion galaxies across a sphere 46 billion light-years in radius. The total universe, if inflation occurred, is vastly larger still. Why so much? Why not a universe that is only a few light-years across, containing perhaps a single star and a few planets? From a purely logical standpoint, such a universe would be much simpler and would seem to require much less explanation. The existence of a small, simple universe seems like it would be easier to account for than the existence of a large, complex one. And yet the universe is enormous. Why? The answer is time. The universe is as large as it is because it is as old as it is, and it is as old as it is because the processes required to produce observers take a specific minimum amount of time. The universe began approximately 13.8 billion years ago. The first stars formed approximately 100 million years after the Big Bang. The first generation of stars lived, burned, and died over timescales of millions to hundreds of millions of years, scattering the heavy elements synthesized in their cores into the interstellar medium. The second and subsequent generations of stars formed from this enriched material, and it took several generations of stellar birth and death to enrich the interstellar medium to the level of metallicity required to form rocky planets with the chemical complexity needed for biology. The solar system formed approximately 4.5 billion years ago, roughly 9 billion years after the Big Bang, by which time the local interstellar medium had been enriched by enough stellar generations to provide the right chemical inventory. Life appeared on Earth within the first billion years of the planet's existence. Complex multicellular life took another 3 billion years to develop. Intelligence, in the specific form capable of measuring the universe, took another 500 million years beyond that. Add all of this up, from the Big Bang to the first observers who could ask questions about the universe's scale, approximately 13.8 billion years. And since the universe has been expanding throughout this time, at the specific rates determined by the succession of radiation-dominated, matter-dominated, and dark energy-dominated eras, the observable universe has grown to its current radius of 46 billion light-years. The universe is this large not because largeness is an end in itself, but because producing observers requires time, and time means expansion, and expansion means size. A universe that was only 1 million years old would be far too young for heavy elements to exist, let alone for planets and biology and minds. The size of the observable universe is therefore directly connected to the time required to produce observers, which is in turn determined by the rates of the relevant physical processes, stellar evolution and chemical enrichment and biological evolution. This connection between the size of the universe and the conditions for observers was noted by the physicist Robert Dicke in 1961, in a brief but important paper responding to Paul Dirac's earlier observation that the universe's age, measured in atomic time units, was approximately equal to the ratio of the electric force to the gravitational force between a proton and an electron. A numerical coincidence that Dirac thought was too precise to be accidental, and that he argued must reflect a deep physical relationship. Dicke's response was to point out that the relationship is not a coincidence but a selection effect. We observe the universe to be of a specific age, because observers can only exist when the universe is old enough for stellar nucleosynthesis to have produced heavy elements, and young enough that stars are still burning. The ratio of the electric force to the gravitational force at the time of our observation is determined by the timescales of stellar evolution and the laws of physics that govern them, not by any fundamental relationship between electricity and gravity. Dicke's argument is an early version of what has come to be called the anthropic principle, the observation that the properties of the universe we observe are constrained by the requirement that observers exist to observe them. The anthropic principle in its weak form is simply the observation that any universe we observe must be one in which observers can exist, which is a tautology, but a useful one when applied to apparent coincidences like Dirac's. In its strong form, the anthropic principle makes claims about why the physical constants of the universe have the values they do, arguing that the values are constrained by the requirement that they permit the existence of observers, which requires them to fall within specific ranges. The strong anthropic principle is more controversial and more speculative, and its evaluation depends on whether the multiverse is real, whether there are many universes with different physical constants from which ours is selected by the anthropic filter. The connection between the size of the universe and the conditions for observers has a specific quantitative form that is worth tracing through. The age of the universe is related to the size of the observable universe through the expansion history. As we have discussed, the age of the universe is approximately 13.8 billion years because the physical constants governing stellar evolution and chemical enrichment and biological evolution are what they are. If the gravitational constant were stronger, stars would burn faster and have shorter lifetimes, and the timescale for stellar nucleosynthesis and chemical enrichment would be shorter. If the fine structure constant, which governs the strength of electromagnetic interactions, were different, the chemistry of life would be different, and the timescale for biological evolution might be different. The specific age of the universe at the moment observers first appear is determined by the physical constants, and the size of the observable universe at that moment is determined by the age. The fact that the observable universe is 46 billion light-years in radius is therefore not an arbitrary fact about the universe. It is a consequence of the physical constants having the values they have and of the time required for those constants to produce observers. In a universe with different physical constants, the first observers might appear at a different time, and the observable universe at that time would be a different size. The specific size we observe is the size corresponding to our specific physical constants and our specific evolutionary timescale. This relationship between size and observer production is part of a broader set of relationships between the physical constants and the conditions for complexity that has been the subject of extensive study in the field called fine-tuning, or the anthropic landscape. The physical constants of the standard model of particle physics, including the masses of the elementary particles, the coupling constants of the fundamental forces, and the cosmological constant, appear to have values that are precisely tuned to permit the existence of complex structures and observers. Small changes in any of several of these constants would produce a universe in which atoms cannot form, or in which stars cannot burn for long enough to produce heavy elements, or in which the universe collapses before structures can form, or in which the universe expands too rapidly for matter to clump under gravity. The most striking example is the cosmological constant. The observed value of the cosmological constant is approximately 120 orders of magnitude smaller than the value predicted by quantum field theory for the vacuum energy density. This is the cosmological constant problem we discussed in the empty space video. The observed value is not zero, but it is extraordinarily close to zero relative to the natural scale of the vacuum energy. If the cosmological constant were much larger than its observed value, the accelerating expansion it drives would have occurred much earlier in the universe's history, preventing matter from clumping under gravity and preventing the formation of galaxies, stars, planets, and observers. If it were much more negative, the universe would have recollapsed into a big crunch before structures could form. The observed value falls within a narrow window that permits structure formation and observer existence, and this window is extraordinarily narrow relative to the range of values that quantum field theory would naturally suggest. Steven Weinberg, in 1987, used the anthropic principle to predict the value of the cosmological constant before it was measured. He argued that the cosmological constant must be small enough to allow galaxy formation, but could be as large as the limit set by this constraint, and he estimated that the largest value consistent with galaxy formation was roughly 120 orders of magnitude smaller than the quantum field theory prediction, but non-zero. When the accelerating expansion was discovered in 1998 and the cosmological constant was measured, its value was found to be within the range Weinberg had predicted, roughly 100 times smaller than the maximum value consistent with galaxy formation. This is one of the few successful quantitative predictions of the anthropic principle, and it is taken seriously as evidence that the anthropic selection effect is physically relevant. The anthropic argument for the cosmological constant, and more broadly the idea that the physical constants are selected by the requirement that they permit observers, makes most sense in the context of the multiverse. If there exist many universes with different physical constants, and if observers can only exist in universes with constants in the right range, then the fact that we observe constants in the right range is explained by the selection effect. We are in a universe that permits observers because only universes that permit observers are observed. The multiverse provides the ensemble from which the anthropic selection operates, and the observed values of the physical constants are the ones selected by the anthropic filter from the full distribution of possible values across the multiverse. Whether the multiverse is real, whether the anthropic argument is a genuine physical explanation or a tautology dressed up in cosmological language, is one of the most contested questions in contemporary philosophy of physics. Critics argue that the anthropic principle explains nothing because it does not predict what values the physical constants will have, only that they will fall within the range that permits observers. A theory that merely says the universe must be able to contain observers is no more predictive than saying the universe must be the way it is in order to be the way it is. Supporters argue that the anthropic principle, combined with a specific model of the multiverse and a specific measure over the ensemble of universes, does make predictions, as Weinberg's calculation of the cosmological constant demonstrates, and that the success of those predictions is evidence for the multiverse. The debate is unresolved and may be permanently unresolvable because the multiverse is not directly observable, and the predictions of the anthropic principle depend on the assumed distribution of constants across the multiverse, which itself depends on theoretical assumptions that cannot be independently tested. What is clear is that the fine-tuning of the physical constants for observer existence is a genuine feature of the universe that requires explanation, and that the two main explanations, the anthropic multiverse and the possibility of a yet undiscovered fundamental theory that predicts the observed values of the constants from first principles, are both serious scientific and philosophical proposals that are actively investigated. The specific relevance of this for the concept of distance is the following. The 46 billion light-year radius of the observable universe is not just a number that happens to be large. It is the specific number that corresponds to the specific age of the universe at which observers first appear, given the specific physical constants that govern stellar evolution and chemical enrichment and biological evolution. The size of the observable universe is therefore connected to the conditions for observer existence in a way that is not accidental but structural, a consequence of the physical laws and the time they require to produce minds. This means that any observer who measures the scale of the observable universe will find it to be approximately the size ours is, not because of any coincidence or conspiracy, but because the size is determined by the time required to produce observers and the expansion history of the universe. In a universe with the same physical constants and the same expansion history, but with observers appearing at a different time, the observable universe would be a different size. In our universe, the size is what it is because the production time is what it is. The universe is large because we are late, and we are late because complexity takes time. There is a specific way in which this connection between scale and observer existence changes the emotional register of the universe's size. The size is not arbitrary. It is not a brute fact that has no further explanation. It is connected to us, not in the sense that it was designed for us, but in the sense that the same physical processes that produced us also determine the size of the region we can observe. The universe is as large as it is because the laws of physics are what they are, and those same laws produce the chemistry and the stellar evolution and the biology that eventually produced minds capable of measuring the universe. The measurement and the thing measured are products of the same physical laws applied over the same timescale. The observer and the observable universe are not independent. They are co-produced by the same physics. The night sky, which looks so large and so cold and so indifferent to anything human, is in this sense precisely scaled to the existence of the observers who look at it. Not because it was made for observers, not because the scale was chosen to be appropriate for human eyes, but because the same physical laws that determine the scale also determine the conditions under which observers could emerge. The universe is as large as it is for the same reason that we exist at all. Because the physical constants are what they are and time has passed in sufficient quantity for both the expansion and the emergence of complexity to have occurred. This does not make the universe small or familiar or easy to comprehend. The 46 billion light-year radius is still incomprehensible in any intuitive sense. The 2 trillion galaxies are still a number that has no experiential analog. The four-dimensional archive of photons arriving from every epoch of the universe's history is still more than any human mind can hold simultaneously. The universe is not scaled to human comprehension. It is scaled to the physical processes that produce observers, which are the same processes that produce minds, but the minds that result are not guaranteed to find the scale comprehensible. They are guaranteed to exist within the scale, which is a different thing. What the mind can do, even if it cannot comprehend the scale intuitively, is understand it structurally, trace its connections, map its implications, and find in the structure something that is more satisfying than mere comprehension would be. Comprehension is passive, the simple act of holding something in mind. Understanding is active, the tracing of relationships and the recognition of structure. The universe's scale is too large for comprehension. It is not too large for understanding. And the understanding that the scale is connected to the conditions for observer existence, that the distance to the edge of the observable universe is as far as it is because the time required to produce observers is as long as it is a piece of structural understanding that changes the texture of the numbers without making them smaller. The numbers remain large. 46 billion light-years is still 46 billion light-years. a distance that cannot be traversed, that no signal we could send would ever cross in any timescale relevant to any concern we could have. The 2 trillion galaxies remain 2 trillion galaxies, each one a collection of hundreds of billions of stars, each star a nuclear furnace producing the light and the heavy elements that make chemistry possible. Each planetary system, a potential site for the emergence of the kind of complexity that can ask questions about the universe. The scale remains what it is. What changes is the relationship between the scale and the observer, which is no longer a relationship of incomprehensible largeness and negligible smallness, but a relationship of co-production by the same physical laws over the same timescale. The specific galaxies in the night sky, the ones visible to the naked eye and the ones visible through telescopes, and the ones visible only through the most sensitive instruments ever built, are not decorations placed at specific distances for the convenience of earthbound observers. They are the products of the same gravitational instability that also produced the Milky Way and the solar system, and the Earth, and the conditions for life. The density fluctuations in the early universe that grew into those galaxies are the same fluctuations that grew into the local overdensity that produced the Milky Way and the solar system. The photons arriving from those distant galaxies cross the same expanding space that the photons from the Sun cross in 8 minutes to reach the Earth. The physics is the same. The scale differs by a factor of 1 billion or so, but the physics is the same. The light arriving from a galaxy 12 billion light-years away left that galaxy 12 billion years ago, when the universe was less than 2 billion years old, and the Milky Way and the solar system did not yet exist. The atoms in that light, the photons whose wavelengths encode the spectral lines of hydrogen and helium, and the heavier elements synthesized in that galaxy's stars, have been traveling through the expanding space for 12 billion years, crossing a proper distance that has grown from whatever it was at emission to 12 billion light-years at reception, being redshifted by the expansion from whatever wavelengths they had at emission to the longer wavelengths at which they arrive. They are ancient photons, carrying ancient information, from a galaxy that existed before our solar system formed, from an epoch of the universe that we cannot directly visit, but that we can read in the wavelengths of these arriving photons. Tonight, right now, those photons are arriving, not as a metaphor. Literally, in this moment, photons from galaxies 12 billion light-years away are crossing the Earth's atmosphere and reaching the surface. If you are outside under a dark sky, some of them are reaching your retina, stimulating the rod cells that are sensitive to faint light, producing the visual signal that the dark-adapted eye registers as a faint smear of light in the direction of certain galaxy clusters. If you have a telescope, you can collect those photons more efficiently, build up the signal over minutes of exposure, and see the individual galaxies whose photons are arriving. If you have a spectrograph, you can spread those photons by wavelength and read in the resulting spectrum the redshift and the chemical composition, and the stellar population of the distant galaxy that emitted them. The act of observation is a physical interaction between ancient photons from distant galaxies and the matter of which you are composed, a direct physical connection across 12 billion light-years of space and 12 billion years of time. The connection is not metaphorical. The photon that reaches your retina was emitted by an electron transition in a hydrogen atom in a star in a distant galaxy 12 billion years ago, has been traveling through the expanding space since before the Sun existed, and has just now encountered the molecules of your retina and transferred its energy to them, producing the neural signal that your brain registers as a faint point of light. The physical chain from the distant hydrogen atom to your visual cortex is direct and unbroken, mediated by the electromagnetic field that pervades all of space and carries information at the speed of light. This direct physical connection between the observer and the most distant observable objects is one of the things that the concept of distance, for all its fragmentation and ambiguity, is ultimately pointing at. Distance is the measure of the degree of physical separation between two things, the quantification of how indirect their physical interaction is, how long it takes for influence to travel between them. And at cosmological scales, where the physical interaction is mediated by photons that have been traveling for billions of years through expanding space, the multiple distance measures are multiple ways of quantifying different aspects of the physical relationship between the observer and the observed. The light travel distance tells you how long ago the photon was emitted, how ancient the information is. The proper distance tells you how far away the source is right now, how disconnected it currently is from your location in the expanding universe. The luminosity distance tells you how much the expansion has diluted the energy of the arriving photons, how faint the source appears relative to what it would appear if the universe were not expanding. The angular diameter distance tells you how large the source appears in the sky, how much spatial information the arriving photons carry about the source's structure. All four measures are aspects of the physical relationship between the ancient photon and the observer who receives it, and together, they give a complete picture of the four-dimensional relationship between the event of emission and the event of reception in an expanding spacetime. The universe's scale is not separate from the observer who measures it. It is the universe as experienced by an observer in a specific location at a specific time, receiving photons from specific distances and specific epochs, embedded in a specific point in the cosmic web at a specific moment in the stelliferous era. A different observer at a different location would measure the same cosmological parameters and the same laws of physics, but would receive different photons from different specific galaxies, and would find a different specific configuration of the observable universe, centered on their location rather than ours. The observable universe is observer-centered by construction, and its specific contents depend on where the observer is and when the observation is made. This observer-centeredness of the observable universe is not a limitation of our perspective. It is a feature of the causal structure of spacetime, the fact that all observations are local events, occurring at specific points in spacetime and receiving information from the causal past of that point. There is no view from nowhere in physics, no observation that is made from outside the universe or from a privileged vantage point that sees all of space simultaneously. Every observation is made from somewhere at some time, by something that is itself part of the universe being observed. The observer is always embedded in what is observed, always a local event in the spacetime whose global structure they are trying to map. This is the final implication of the universe's scale for the concept of distance. Distance is not just a property of the universe. It is a relationship between the universe and an observer embedded in it. The four distance measures are four aspects of this relationship, four ways in which the expansion of the universe and the finite speed of light and the specific expansion history combine to produce different physical effects on the photons traveling between the source and the observer. The universe's scale is always the scale as seen from here, from this specific location in the cosmic web, at this specific moment in the history of the expansion, by this specific kind of observer whose existence is itself a product of the same physical laws that determine the scale. The night sky tonight is the universe as it appears from this specific here and this specific now. The stars and galaxies visible in it are the ones whose light had time to reach this location by this moment. The distances to them, all four measures of those distances, are the distances as determined by the expansion history of the specific universe we inhabit and the specific values of the physical constants that govern it. And the mind measuring those distances, finding them too large for intuitive comprehension but not too large for structural understanding, is itself a product of the same expanding universe whose scale it is attempting to measure. The universe is so big the word distance has stopped making sense. That is true. The word has fragmented into four different things that all mean something slightly different and all give different numbers. But the fragmentation is not a failure. It is the universe being more than the word can hold, requiring a richer vocabulary, a more precise language, to describe what it actually is. The universe is large enough to require 4 distance measures instead of 1. It is old enough to have produced observers capable of discovering this requirement. And the specific largeness and the specific oldness are the same fact, the same consequence of the same physical laws applied over the same span of time. This is what the night is for, not for comprehending the incomprehensible, which the scale of the universe certainly is, but for understanding the structure of what cannot be comprehended, for tracing the relationships that connect the large to the small and the ancient to the present, for sitting with the specific fact that the photons now arriving from the farthest observable galaxies left their sources before the sun existed and have been traveling through the expanding space ever since, and that right now, in this specific moment that is tonight, they are arriving here at this location, interacting with the matter of this place, and producing the faint light that is the universe reporting on its own past. The universe rewards precision. It rewards the effort to ask the right questions in the right language. It rewards the development of mathematical tools that extend human cognition beyond its evolved limits. And it rewards the specific quality of attention that the night provides, the attention that is patient enough to trace the relationships rather than grasping for a comprehension that the scale does not permit. The night is long enough for this kind of attention. The universe is old enough to have produced it. The distance from here to the edge of the observable universe is exactly as far as the universe's expansion has had time to carry things in the time it has taken to produce the kind of matter that measures distances. That is where we are. That is how far away everything is. That is what the word distance has become and what it points at, and why it is worth the night to follow it all the way to the edge. Thank you for spending this night with the scale of things. This is dusk and discovery. The observable universe is 46 billion light years in radius, and you are exactly in the middle of it. Sleep well.